Okay, one additional thing that I would like to present is the following. You have already, if you consider have you already seen this expression to represent identity? So the combination of brackets of all the levels to have, okay. So the idea is now to just see what happens if I use that base, if I use that identity to change the representation of the levels from one base to another base. So in case, let's say, let's suppose that the vector k represents the system using one set of levels. Then we change the base, we change the representation, and use another set of levels. I call those levels lambda, but any letter may be fine in this case. So we have lambda, a lambda that is identity, and then we have level k. Due to the fact that the representation of the cat k can be seen as a construction operator corresponding to level k applied to vacuum. And this is equal to the sum over lambda of lambda k, and this is just the scalar product between one of the vectors lambda and one of the vectors k, times vector lambda can be seen as a construction operator corresponding to level lambda applied to vacuum. So in this case, you have that the operator on the left is equal to the result of the application of this operator to vacuum is exactly equal to the result of the application of this operator to vacuum. So you may say that C cross K is equal to sum over lambda of lambda K C cross lambda. And in case you do not consider the construction operator, but you consider the distraction one, then you have the same you have the same connection between the those two operators. You have always this scalar product here. The only difference is that in that case, the scalar product is you have the complex conjugated. You do not have lambda k, but you have k lambda because you consider the in this case, the initial state is not on the cat side, but is on the brass side. So this is to say that up to now, I have always represented the levels using the wave vector representation. So I have all the levels indexed by, for instance, wave vector k, and I have arranged all the levels according to that, or to the ordering applied to k. But one interesting result can be obtained if we switch from the wave vector representation, that is the, let's say, reciprocal space representation that we have used up to now, to another representation that is the one corresponding to the coordinates. So for the moment, we have said, okay, level k can be occupied or unoccupied. Another way of describing the same thing is position x is occupied or is not occupied. So in this way, it's possible to switch from let's say, to use a continuous basis, because if you use the representation of the coordinates, in this case, the index, let's say, is the position. So you have a continuous index that may change depending on the position of the electron you consider. And in this case, if we call x the state that corresponds to there is one electron in position x, and we apply exactly the same formalism, but with the wave vectors with the wave vector representation. So as an identity, we use all the vectors corresponding to the wave vector representation. Then we may apply the same approach that we have used before. So in this case, we have a cat with vector k, and we may say that the cat with vector k is the result of the application of the construction operator corresponding to level k to vacuum. Then we have kx. What is this? This is the projection of particle in position x to the state k. In general, if you project, if you project one level over a position, what you find is the wave function, because it's just like as if you said, I have level k, I want to see the projection of that level on that position. The result of that application is the value of the wave function over that specific position. So here you have the opposite. You have not the scalar product xk, but you have kx. So you have here, you have the complex conjugated of the wave function. So this is phi of k of x conjugated. And this is equal to what? Is equal to the application to vacuum of, let's say, the construction operator that builds up one electron in position x. In general, this construction operator is represented with an expression that resembles the fact that here you have a wave function. So you represent that as a wave function, but with a hat to say that it's not a wave function, that is an operator, with the cross, because we are in need of a construction operator, and this construction operator refers to position x. So at the end, we have that we may define a construction operator corresponding to position x as phi k conjugated in position x times c cross k. If you notice, this is an operator that, we have now an expression, and this expression includes here all the construction operators that correspond to the levels. Here we have the wave function of corresponding to each level. So we have built up a correspondence that to each position in space associates an operator. So in this way, let's say if you consider, for instance, the electric field, in that case, you have a field that associates to each position in space a vector. The wave function is a scalar field because to each position in space you associate just a scalar number. In this case, you have a field operator because you associate to each point in space an operator. So this is what is called a field operator. Since in this way, we create the correspondence between, again, a position in space and an operator corresponding to exactly the same position. And at this point, we may imagine what is the distraction operator. The distraction operator is just has the same expression, just with the complex conjugate of that. So in this case, the distraction operator is the sum over all the levels of phi k of x without the conjugation, ck. So in this case, using exactly the same method, it's possible to build up also the field operator, that is the distraction operator corresponding to position X. And if you notice here the structure of those operators, since you do not concentrate your attention on the level, but you concentrate your attention on the position, to create an electron in position X means to make a combination of all the contribution of all the wave functions evaluated in the same position. So it's just like as if you were evaluating this superposition of all the possible level in just one point in space. And that gives you the opportunity to create one particle there. That is, again, the contribution of all the levels included in the system evaluated in that specific position. And just to see that using the anti-commutation relationships regarding operators C cross K and CK, we may have exactly the same result also corresponding this in the case of these field operators. Let's just try to see what happens if we consider the anti-commutator of psi cross X and psi cross X prime. So it's just like as if we were considering the in this case, what changes from one operator to the other operator is not the index of the level, but is the position. So here we have X, and yet on the other side we have X prime. So if we write that using the expressions we have here, we have a sum over K and K prime of the first operator is given by phi K conjugated evaluated in X C cross K, and then we have the second operator. In this case, we have phi of K prime conjugated evaluated in X prime, and we have C K prime. Then we have the second part of the anti-commutator, so we have to sum again K prime. In this case, we have to switch the order, so we have phi K prime conjugated X prime and CK, sorry, I forgot the cross here. We have C cross K prime. Then again, also here, C cross K prime, phi K conjugated of X, C K cross. At this point, we may collect the summation over K and K prime. Due to the fact that the wave functions are just numbers, we may group the numbers and leave the operators on the other side. So we have here phi K conjugated evaluated in X times phi K prime conjugated evaluated in X prime. And then we have C cross K, C cross K prime plus C cross K prime, C cross K. And this is exactly the anti-commutator of C cross K prime, that is 0. So the final result here is that we have 0. So making exactly the same steps, it's possible to see that all the anti-commutators that we use for the levels expressed in the base of the corresponding to the operators that are expressed using as a base the base of the levels are also found when we use the operators that are defined using as a base the base of the coordinates, so the base of the positions. What I would like to just to make another example that helps me to introduce a new way to handle these operators that are defined in the position space is the following, just to check that also the number of particles, the occupation, the occupation number of one level operator that was defined as in this way as an equivalent using the operators defined in the base of the coordinates. So let's just try to see what happens when we use the psi cross psi cross x times psi x. In this case, we have the summation over, again, k and k prime. The construction operator corresponding to position x is phi k conjugated position x ck cross, and then we have the phi k prime without conjugation position x ck. And again, due to the fact that the wave functions are just coefficients, we may write this as phi k conjugated of x phi k prime of x, and then we have c cross k c, sorry, there is a k prime here, ck prime. Now, this resembles a sort of scalar product between the wave function of level k prime and the wave function of level k. But to, let's say, to have the scalar product, I should perform the integral over the whole space. So if I make that integral, so if I evaluate this expression, then I have a sum of k and k prime, an integral in d3x over full space phi k conjugated of x phi k prime of x, and then the two operators that are out of the integral. This is actually the scalar product of those two levels, and if we choose the levels to be, if we choose the wave functions of the level to be orthogonal with each other, this integral is different from zero only if k is equal to k prime. So the fact that we require the integral to be different from zero gives us a constraint corresponding the indexes of the levels. So in this case, we require that k is equal to k prime, so we may drop the double index of summation here. Having this information in mind, we may apply this constraint also on this summation. So having the fact that we need to perform the integral in mind, we may rewrite this as sum over k of phi k x square modulus c cross k ck, and this is the number of particle operator. So we may rewrite that as sum over k of phi k x square modulus number of particle operator. And in this case, if we now go on with the evaluation of the integral, we have the summation of over k of d3x. Then we have the square modulus of this wave function, and then we have the number of particle operator. If the wave functions are chosen so to have a square modulus that is equal to 1 over the full space, then this integral is just 1. So we have a summation over k of nk. So this is at the end, the total number of particles that we have in the system. Due to that, so due to the fact that the integral over the full space of this psi cross x, psi x operator is exactly equal to the total number of particles that you have in the system. And as we have obtained the total number of particles by making an integral of something multiplied by a volume element, this is a sort of density. Because if this was a sort of number of particles per unit volume, then we multiply by the volume and we have the number of particles. So in this representation, psi cross x, psi x can be described as a density of particles evaluated in position x. So this is the particle density. So due to the fact that we do not use a discrete basis, and if we use a discrete basis, we have a specific number of particles for each index corresponding to this discrete basis. Here we use a continuous basis, so we have a density corresponding to the actual number of particles, and that density can be defined as psi cross x, psi x, in a way that is quite similar to the definition of the number of particles operator that we defined as C cross K, CK, when making reference to the discrete basis that was the basis of the levels. And okay, so this shows us that if we use the discontinuous basis, and if we use the field operator representation to describe the creation of or the destruction of one electron in a specific position, then by using an expression that is quite close to the similar expression that you would have used with the wave functions, because at the end, just to make a short comparison, if you consider this expression, what is the equivalent expression in first quantization? The equivalent expression, so this is a second quantization expression because we use vector field operator. But what is the equivalent of that in first quantization? The equivalent of that is the expression that is based on so in general, the square modulus of a wave function represents the density, the probability density to find one electron in that position. So if you make this integral, this is the equivalent of the probability density to find one electron in position x, then you multiply by the volume element, and then you make the integral over the full space or over the volume you are interested in to evaluate the probability to find the electron. Here you make something that is very similar. You make an integral with the creation and destruction operators that are the equivalent of wave function and the conjugated of the wave function to find the, let's say, the density of the operator density in the using this vector field formalism. So the underlying idea is if we use with those operators the equivalent of the expressions that were used in the first quantization, we may expect to find exactly the same result, but not in terms of scalar quantities, but in terms of operators. So as like here, you may obtain the density to find an electron in position x using just the wave function that is a scalar field. On the other side, in second quantization, you have the corresponding field that is a vector field operator that corresponds to, in a similar way, to a density operator. So you have the density operator that tells you what happens in the position space representation, in the coordinates representation when you consider the operators. Due to that, we may try to see what happens if we want to represent the, and this is the final point of the discussion, because if you remember when I introduced to you this later determinant, after discussing the details of the determinant, what I tried to do was to evaluate the expectation value of the different operators over that determinant. And at the end, we found that for one-body operators, nothing changed with respect to the, let's say, Hartree approach, while for two-body operators, we had this a specific change with respect to the Hartree representation. So what I'm going to do now is to apply exactly the same procedure. So using this correspondence between first quantization approach and second quantization approach for what concerns the formalism, try to write in second quantization the equivalent of the expectation value of one operator using the first quantization approach, and then see what happens. So the idea is, if now using the same representation, I use A1 as a one-body operator, if in first quantization your idea was what is the expectation value of that operator over one level, you would have written the integral over d3x level x conjugated one-body operator psi x. You make the calculation, you find the expectation value. So if we now want to use the same approach using second quantization, we may write down exactly the same equation, but replacing the, let's say, the scalar field that corresponds to the wave function in this expression with the vector field that corresponds to the creation and destruction operators using the second quantization formalism. So the equivalent of this expression is the following. That is the, so we have d3x. Now we have the psi cross x, so the field operator corresponding to position x, one body operator, psi x. The difference is that in first quantization, the result of the expectation value is a number. That may be the energy if you consider the energy, the Hamiltonian. That may be a velocity if you consider the momentum operator, and so on. In this case, as we are making an integral with operators, the final result will not be a number, a scalar, but will be an operator. So what we will obtain at the end of this calculation is just an operator. So in this case, what we may do is just to rewrite C cross X psi x as a sum over k and k prime. We have the integral d3x, then we have phi k conjugated in position x. Now I keep all the numbers and all the wave functions on one side, and I put the operators on the other side. So here I have the one body operator, and then I have level phi k prime evaluated in position x, and then I have C cross k C k prime. So if you notice here, this is just the matrix corresponding to the expectation values of the A1 operator over all the possible levels. So we may write this as sum of k prime, one body operator k prime, and then we have C cross k C k prime. If A1 is diagonal over the wave vector basis, that means if this matrix here is diagonal, then this summation reduces to just one index, because all the elements where k is not equal to k prime are 0. So we have one body operator k, c cross k, c, k. And this is the number of particle operator. So we have summation over k of one body operator k, and of k. Just to make an example, if the one body operator is the kinetic one, and at this point, what is this matrix? Sorry, matrix. What is the value of those elements? Those elements are the expectation value of the operator when you consider, let's use just the free electron picture. So the evaluation is quite easy. So in this case, this is just the expectation value over the kinetic energy operator over a plane wave. So this is equal to a summation over k of h bar k, k squared divided by 2m times the number of particle operator. And as you see here, if, for instance, this represents the total energy, the total kinetic energy of the system, because at the end, we just sum up over all the possible levels that can be occupied or unoccupied depending on the expectation state of nk. So the idea is, if we apply this operator to this vector, and this vector is the Fermi sphere. So the Fermi sphere, so this is the Fermi So the Fermi sphere completely filled, 0 Kelvin, just a sphere of including the field levels, and all the empty levels are out of the sphere. At this point, what is the expectation value? So if we apply that to, if we evaluate sum over k of so if we apply that to the Fermi station, to the Fermi sphere, at this point, the expectation value of n over the Fermi sphere is 1 if k is within the Fermi sphere, 0 if the Fermi sphere is outside. So this reduces to a sum over k modulus smaller or equal to kf of h bar squared k squared divided by 2m. That is just the total energy of the system. Sorry, that is just the total kinetic energy of the system if we consider plane waves. So the idea is, in this way, we have started with a general expression for a one-body operator, and we end up with an operator. Just to make an example, we try to substitute this arbitrary one-body operator to the kinetic one. So due to the fact that the kinetic operator is diagonal over the plane waves, then we have this expression for the matrix elements of the operator over the basis of the plane waves. So the representation of the operator, the final operator, using the second quantization approach is quite simple, since we have just this coefficient times the number of particle operator corresponding to level k. Just to make sure that everything is fine, we applied this operator to the Fermi sphere, that is all occupied levels up to EF, and then just empty levels. So if we apply that operator to the Fermi sphere, the expectation values of nk, that is the expectation value of n is equal to the Fermi-Dirac distribution evaluated at the energy of the level, and in this case, the energy of the level is this value here. Due to the shape of the Fermi-Dirac distribution at 0 Kelvin, that is just a step function that switches from 1 to 0 as soon as we cross the Fermi energy. So that reduces, by considering the expectation values, that reduces to the summation over k modulus smaller than equal to kf of this term here. And this is the same integral we resolved when we considered the Sommerfeld model. Sì. Yeah, there was a question by concerning the effect of Fs. In this case, whatever the whatever respectively of the state you put here. So here I just used the Fermi sphere to simplify the calculation, but in case we use not the Fermi sphere but another state, just an arbitrary how may I write here? I'm sorry for this representation. So if here we represent an arbitrary electronic state at temperature T different from 0, always for free electrons, at this point I may not say that the Fermi-Dirac distribution is just a step function, because there is a smooth transition from occupancy 1 to occupancy 0 into the into F. So at this point, I may not just apply a cutoff to the summation and say only the wave vectors up to kf contribute to the summation. So in principle, this transforms to a sum over k where there is no limitation, no upper boundary on k of the energy times F. And in this case, F is evaluated at the energy corresponding to the level. And this is transformed into an integral over d3k 4 pi to the power of 3. Then we have the energy and also F of E of k. So this is the usual integral we met using the Sommerfeld model. So this comment was at the end concerning the possible boundaries over the summation due to the application of this operator to the final state. And the answer at the end is yes, in the sense that in this configuration, depending on the free electronic state, the only thing that may change is the value of the limits of this integration. If t is equal to 0, the integral is from 0 to kf. If t is different from 0, there is no upper boundary for the integration. K modulus may go from 0 to infinity because the Fermi-Dirac distribution considers the occupancy of the levels and so applies the cutoff when the levels are unoccupied. So again, the final point is, if I use exactly the same formalism that comes from the first quantization and I just replace the wave function that I had in the first quantization with the field operator that I have in second quantization, I may obtain new operators that allow me to evaluate the general quantities, velocities, energies, and so on over the system by using the second quantization approach. Next Monday, I will make the same evaluation, not by using a one-body operator, but using a two-body operator. So I would try to use this formalism to handle the situation where where we consider the effect of the electron-electron interaction, that is a two-body operator, over the energy of the system. So the idea is to see whether, without making any assumption concerning the electronic wave function, because as you see today, I have never introduced Slater determinants or introduced any symmetry or anti-symmetry in the system, we will see whether with this different approach, we may recover the results that we obtained with the Hartree-Fock method, that is the presence of a direct term and of the exchange term in the energy resulting from the electron-electron interaction. Okay, do you have questions or comments? Okay, if not, I stop the registration, and I also switch off the connection, and in a while Professor Moretti will start a new one from the quantum mechanics lesson. So goodbye, see you next Monday, and please remember then on next Tuesday there will be not the solid state physics class. So goodbye.
Arrivederci, prof.
Arrivederci.